From Delft, and this is a joint work with my collaborator Niederreiter from Fraunhofer Institute and SIT in Germany. And today I'm going to present a hardware-based Niederreiter cryptosystem which uses binary Goppa codes. So first, a very brief overview about the code-based cryptography. As we all know, nowadays, due to the arrival of quantum computers, we have a new type of public key cryptography called post-quantum cryptography, and they are based on different types of hard programs. And in our implementation, we focus on the code-based cryptosystems, which was originally proposed by Max in 1978, and the later variant was proposed by Niederreiter in 1986. In the original proposal, he used generalized Solomon code, which has been broken. But later, the efforts with Goppa codes, they remain secure nowadays. Afterwards, people tried to introduce some structures into the code, for example, the QC and GPC code, but they all have decoding errors which would limit their use cases. Therefore, in our implementation, we focused on the Goppa code-based Niederreiter cryptosystem. And before talking about the actual design, I'd like to give some motivation for why we are doing such a big code-based scheming hardware. First of all, the reason is code-based schemes, they are very well understood nowadays, based on the fact that it has a very long history of research. A lot of cryptanalysis work has been done, but no critical errors has been found yet. And its security parameters are very widely accepted nowadays. And we know that code-based schemes, due to the complex operations, especially in its key generation part, is very expensive to implement it in software. Therefore, if we have a dedicated hardware design, which includes a code-based scheme on top of it, we can make them much more practical for real-life use cases. And also, one selling point for hardware design is that it can be very easily parameterized. You can choose to allocate more logic or less logic depending on different use cases. So next, I presented a very brief review for the coding theory which would involve in the whole cryptosystem. So we used the Niederreiter cryptosystem based on binary Goppa code. How do we actually define a binary Goppa code? It can be determined by two parts. The first is a degree T Goppa polynomial. All of its coefficients are chosen from a binary finite field shaped to the n. Afterwards, you need to pick the code locator, which is composed of n distinct elements, and each element again is chosen from the finite field. And then the code itself can be defined by the parity check matrix, which is uniquely determined by Gx and the code locator L here. And whenever you're given a random vector called C, you only need to check the matrix vector product between H and C, and whenever you see the result equals to 0, you can conclude that, okay, this is a valid code word. And once we know the Goppa polynomial G and the code locator L, we would uniquely figure out what the binary Goppa code is. Therefore, we need to keep these two parts secret as the secret key. And we would publish the parity check matrix H as the public key. And for the encryption, in our implementation, we didn't worry about the key encapsulation part. We assumed that we already get an error vector of weight T. And then all we need to do is to compute the matrix vector product between the parity check matrix H and the error vector, and then we would get the syndrome, and afterwards we will publish it as a ciphertext. And for the decryption, the intuition is that we want to recover the error vector out of the given ciphertext, the syndrome, and the secret key. So next, let's take a look at how we actually designed it in hardware. Let's start from the building blocks. So to have the whole thing working on hardware, we need to start from defining the most basic arithmetics. We started from the finite field arithmetics, for example, finite field multiplications, inversions, and so on. And once we get the finite field arithmetic, we started building polynomial arithmetics, for example, polynomial multiplications. And then once we get all these basic arithmetics, we can start defining the higher level functional units. For example, we implemented the random permutation module by use of a merge sort algorithm, and we implemented a dedicated polynomial evaluation module by use of the additive FFT. And also, we built a Gaussian systemizer for example, solving systems of linear equations, which we used to generate the secret Goppa polynomial. And also, we need to implement a decoding algorithm for the decryption part, and we implemented the Berlekamp massing module for doing that. And today I'm going to focus on the merge sort module and the Berlekamp massing module. So first, let's take a look at the random permutation. Let's record that part of the secret key is a code locator, which is composed of n distinct elements chosen from the finite field. Our approach for achieving this is we would first permute a list of 2 to the n elements, and then after the permutation, we would just pick the first n elements from the result. We actually tried 2 operations in our implementation. The first is the shuffling algorithm. Shuffling algorithm, intuitively speaking, it's pretty straightforward. You just need to keep swapping 2 elements at a time randomly, and you just, once you go through the whole list, you can get a random permutation. But the problem with the shuffling algorithm is that it can be very easily biased if you didn't implement it very well. Actually, in our design, we achieved non-biased implementation. But the problem of the implementation is that it's not constant time, because its running cycles will depend on the initial seed that you feed into the module. There are also ways to make it constant time, but that would be very expensive. That's why we tried our first option, which is the constant time merge sort algorithm. So merge sort algorithm, here I would briefly repeat how it works. First, we would sample 2 to the n random 32-bit values. And then we would generate a list of tuples simply by, let's say, appending an index orderly chosen from 0 to the m minus 1, and then append it to the random value. And then, in this case, we would get a list of tuple. And then we start the merging sort process by working on the first element. And then finally, by extracting the second part of the merge sort process, we can get a random permutation. So here I get a number which says 32-bit random values. Actually, this is a parameter that you can choose freely to adjust your collision rate in your implementation. So finally, we achieved a constant time random permutation module, but this module would require much more expensive logic and therefore more cycles. But that's a trade-off that users can achieve between security and the logic consumption. So now let's take a look at the implementation of this merge sort module. Let's first start from, let's say, how to implement the merge sort module in software. Intuitively speaking, what we can do is you can each time pick 2 elements from the memory, and then you compare it. And after the comparison, you write the comparison result back to your memory, and you just keep doing that for the whole list for a fixed number of rounds. And finally, you would get a random permutation, or you would get a sorting result. One second point for hardware is that you can, as I mentioned before, you can allocate the logic freely. Therefore, what I can do in a naive way to speed up the whole computation is that I can, for example, simply duplicate my logic for 4 times, and then by working on 4 chunks of the list in parallel, I can achieve a speed up of 4x times. But in this sense, in hardware, we know that the criterion for judging whether a design is good or not is a time error product. Therefore, in this case, you didn't achieve much because you duplicated the logic by 4 times. Therefore, even if you achieve 4x speed up, it doesn't mean anything. Therefore, we took advantage of the hardware advantage, which is the hardware pipelining, which basically means you can, by timing multiplexing different logical units, you can keep them busy for all the time. And at the same time, you can achieve the 4x time error product. That's what we achieved in our hardware implementation by implementing a 4-stage pipelining module. So next, let's take a look at the efficient decoding algorithm. So this is used for computing the error locator polynomial in the decryption part. There are roughly 2 options. Option 1 is a Patterson algorithm. People all claim that Patterson algorithm is faster than Berlekamp-Massey because it took advantage of some special probabilities within binary Goppa codes. But the problem with this Patterson algorithm is that the algorithm itself is not constant time, and it's not so easy to protect it against timing side-channel attacks. Therefore, we chose to implement a constant time Berlekamp-Massey algorithm, which I will show in a minute. Another advantage for the Berlekamp-Massey algorithm is that it can be used not only for binary Goppa codes, but also for more general alternate codes. So this shows the algorithm that we used for the Berlekamp-Massey part. This is proposed in 1990 by Xu in his paper, and it can easily see that the Berlekamp-Massey algorithm provided here is constant time because, first of all, you can see that the number of loops equals to 2t, where t is one of the security parameter. So of course it's fixed. Therefore, we have a fixed number of loops. And within each loop, we have 2 main operations. First is an entry-wise multiplication, which we built an entry sum module for doing this. And clearly the pattern is very fixed. So it's very easy to implement it in constant time. And the second main operation is the conditional updating. And you can see that although it is conditional, its pattern is also fixed. Therefore, you can also make it very easily implemented within constant time. Therefore, we have a fixed number of loops. We have within each loop, the operations are also constant time. Therefore, the whole Berlekamp-Massey algorithm can be implemented within constant time. So this actually shows the hardware design for this module. First is the entry sum module we defined for the entry-wise vector multiplication, which would involve big vectors. And then we feed it to the stack module, which does a bunch of operations. And the most expensive one within them is the scalar multiplication, which also involves which also involves a big vector. And to accelerate these 2 modules, we took advantage of another hardware advantage, which is a tunable parallelism within it. Intuitively, it can determine, for example, you can choose whether to allocate more or less logic depending on how many coefficients you want to work on within each clock cycle. So now that I have already introduced 2 building blocks, how did we actually build the full hardware design for the 4 Niederreiter crypto system? So this is a diagram showing the key generation, which can be divided roughly into 2 parts, for the secret key and the public key generation. For the secret key, it involves 2 parts. The first is for generating the Goppa polynomial. The second is for generating the random permutation as a code locator. Actually, these 2 parts, because in hardware you have different pieces of logic for doing that, you can parallelize them very easily. And once you get the secret keys, you can feed it to the right side, which would generate the public key for you. And for the encryption, as I mentioned, just a matrix vector multiplication, which can be mapped to very cheap XOR or column-wise XOR operations in hardware. For decryption, that's a more interesting part, but still not as expensive as key generation. You use, for example, additive FFT for evaluating the Goppa polynomial for computing the syndrome, and then you use the decoding part to recover the error locator polynomial. And once you get the error locator polynomial, you feed it back to the polynomial evaluation logic again. By reusing it, you can evaluate the error locator polynomial and recover the message out of it. So that's the high-level idea about the different functional units within the Niederreiter crypto system. So how do we actually evaluate the whole design? We need to make sure that it actually works. This is the setup we had during our experimenting phase. Roughly can be divided into 2 parts. The first is the workstation. The second is an FPGA chip, which includes 5 parts inside it. The first is a UART module, which is responsible for communicating with the workstation. And once the workstation sends some commands to the FPGA via the serial port module, it can start talking to the state machine, which again talks to 3 main modules within the Niederreiter cryptosystem: the key generation, the encryption, decryption. So once the FPGA finishes its operations, it sends an X signal and the computational results back to the workstation through the UART module, and then the workstation will start its verification phase by checking the results from the FPGA with the reference results computed from the software scripts. So how do we actually achieve the flexibility in our design? Because most of our code, they're generated by code generation scripts. Therefore, all the security parameters, they can be freely chosen. And once you fix the security parameters, you can choose what are the design parameters for your design. For example, if you say, I'm targeting at a smart card application, which would require that you pick smaller parameters for that, because there are only limited available resource on top of the card. Or you want to say that I want to use a code-based design in my server accelerator. I don't care about the logic. I only care about the performance. Then you can just pick as big design parameters as you want. This table here shows the design parameters that you can choose in your Niederreiter cryptosystem. So this table is for the recommended parameters for MacLeod's cryptosystem proposed in the PQ Crypto project, which corresponds to over classical 256 bit security level. And you can see that by picking different sets of design parameters, you can satisfy different use cases. For example, here I provide these 3 use cases: area, balanced, and time. Area means I want to use as few logic as possible. Balanced basically means balanced. And time means I want to have a high performance design. And you can see that you can easily achieve a trade-off between the running time and the logic consumption. So one thing which is worthwhile to point out here is the memory usage. You can see that actually for different design parameters, they more or less use the same amount of memory, because in hardware you can configure your memory as you want. So we also compared our design with a few existing work. First, we tried to compare our design with a 2010 paper, which is the only existing work that included the key generation part inside it. We synthesized our design for their parameters, and you can see that we not only achieved a much smaller design, but only achieved a much faster design. And we also tried to compare our design with, let's say, the fastest to date decryption module within the FPGA implementation. I think this is a 2015 paper. Yeah. So you can see that our design achieved a much smaller time error product compared to the design, and at the same time, it's much faster compared to the decryption module. Moreover, we also compared our design with the fastest to date software implementation, which was implemented by Johnny. So by comparison, you can see that our design takes much less cycles compared to the software implementation. And we can figure out that although FPGA runs at around 20 times lower frequency compared to the CPU, we can achieve a very high time speed up, especially for the most expensive key generation part. So to conclude, we provided the first constant time Niederreiter cryptosystem based on our FPGA implementation, which also provides a very high security level. And also performance-wise, it is much faster compared to the software implementation. And also, due to the flexibility of our design, you can just download our open source code and easily choose your own parameters to satisfy different use cases. Thank you for your attention.